You know how sometimes you hear about a new invention, maybe a new idea that just makes you rethink what's even possible?
Yeah, absolutely. Those moments where the rules seem to bend a little.
Exactly. Well, today we're diving into something that could potentially do just that for how we understand, well, the very fabric of reality, specifically electromagnetism.
Wow, okay. Going deep.
We're going to explore the world of extended electrodynamics, or EED.
Right. ED. So think of it like this, maybe. We all, learn about magnets, electricity, right? The
Yeah.
forces Maxwell described over a century ago. Standard stuff.
Sure. Physics 101.
But what if that's, well, not the whole story. What if there are hidden layers, maybe nonlinear behaviors, even connections to other forces like gravity that we haven't fully worked out?
Okay, I'm intrigued.
That's the kind of territory ED starts to map out, and it's based on some really fascinating material you've shared for this.
Exactly. Yeah, you've pulled together some incredible stuff. We've got foundational academic papers, the ones that first really proposed these ideas, but also insights from like cutting edge discussions, things happening now.
Like at the Convergence Summit and that Beyond Conventional Physics podcast.
Right. So our goal today is really to unpack this.
Hmm.
For you listening, try and understand where ED came from, where it is now, and look at some of the really groundbreaking, maybe sometimes a bit out there applications being explored.
And we want to try and pull out the key insights, without getting totally bogged down in the super complex physics equations. Make it graspable.
Yeah, give you those aha moments, hopefully.
And fundamentally, ED is trying to tackle some big questions, like, could we model basic particles, say a photon, not just as this abstract point of energy, but as an actual stable thing, like a structure made purely of the electromagnetic field itself?
Whoa, okay, so the field is the particle, in a way.
That's the kind of thinking. And doing that involves, well, tweaking the equations we have, adding nonlinear bits, maybe even introducing whole new types of fields.
Okay, so it's like a potential upgrade, maybe a significant one, to our operating system for understanding one of the universe's absolute core forces.
That's a good analogy, yeah.
So what were the first hints then? What were the puzzles or maybe inconsistencies that made scientists think, maybe the standard version needs an expansion pack?
That's a great starting point. If we look back at the foundational stuff, Donev's 1997 paper, Introduction to Extended Electrodynamics, that's really key, a cornerstone.
Donev, okay, 1997.
Yeah. He basically proposed ED as a way to extend Maxwell's equations by adding these nonlinear terms. And his specific goal initially was to see if you could model photons as something called solitons.
Solitons, what are those exactly?
Think of like a pulse of energy that holds its shape. It travels without spreading out, without dissipating, almost like a self-contained wave packet.
Okay, like a tiny stable ripple that just keeps going.
Exactly. So Donev's idea was, could the electromagnetic field itself be the stuff that photons are actually made of, structured as these solitons?
So yeah, moving away from the photon as just this abstract point particle and seeing if it could be, I don't know, a persistent pattern in the field.
Precisely. And then his 2004 review paper, Extended Electrodynamics, a brief review that built on this. It synthesized different approaches, relativistic and non-relativistic ways, to describe these self-sustaining waves that have photon-like properties.
So he kept working on it.
Oh, yeah. He and others like D.A. Woodside, A.I. Arbab, these names pop up a lot, often linked with places like the Bulgarian Academy of Sciences or maybe EarthTech International later on. They're definitely key figures.
Right, those names sound familiar from the sources.
Yeah.
So what are the core ideas then? What makes ED really different from classical electrodynamics? What new concepts are on the table?
Okay, let's break down a few main things. First is these nonlinear extensions. In basic physics or math, linear means simple cause and effect, right? A straight line graph.
Double the cause, double the effect.
Exactly. Nonlinear is more complex. The output isn't directly proportional. You can get feedback loops, unexpected behaviors. So in ED, adding nonlinear terms to Maxwell's equations is what allows for those Soliton solutions we talked about, those stable wave packets.
Ah, okay. Linear equations usually just describe waves spreading out, dissipating.
Right. The nonlinearity provides a kind of self-containment mechanism. So it's like
Mm.
adding, yeah, complexity to the rules to let the field do more interesting self-sustaining things.
Okay, that makes sense. What else?
Another really fascinating prediction, especially in some versions like what's called gauge-free ED,
Mm.
is the possibility of scalar fields.
Scalar fields. Okay, what does that mean?
Well, these could potentially manifest as things called scalar longitudinal waves, SLW, or just scalar waves, SW. Now, normally, light waves, electromagnetic waves, they have both electric and magnetic. Right. These scalar waves, though, theoretically, could carry energy and momentum without that magnetic field constraint, or at least behaving very differently.
Whoa. Waves without a magnetic field
Yeah.
or a different kind of field interaction? That sounds fundamentally different.
It is. It suggests electromagnetic phenomena that just go beyond what standard Maxwell's equations typically allow for.
What kind of possibilities could that unlock, or is that jumping ahead?
We'll definitely get to potential applications, but for now, the key idea is it hints at physics beyond the standard model of electromagnetism. And one more concept from Donev is this idea of a scale factor.
Scale factor.
Yeah, it's kind of a mathematical tool he introduced. It helps analyze the rotational, sort of swirling components within these nonlinear wave solutions, which becomes important when you think about how these waves might propagate, how they might interact.
Okay, so non-linearity, potential scalar waves, and the scale factor for analyzing rotation. It feels like a move towards a more, I guess, intricate mathematical picture to capture potentially wider phenomena.
That's a good way to put it.
Now, you mentioned ED really picked up steam late 20th century. What was going on then? What understanding of light or problems were pushing people to look for these extensions?
Well, by the late 20th century, we had quantum electrodynamics, QED. Incredibly successful theory, right? Describes light-matter interactions at the quantum level fantastically well.
The most precisely tested theory in science I think I've heard.
Pretty much. But even with all its success, QED doesn't always give you a simple, clear, sort of classical picture of what a single photon is as a finite, stable object moving through space. There's still the weirdness of particle-wave duality baked in.
Right, the quantum fuzziness.
Exactly. That plus some persistent theoretical headaches within classical electrodynamics itself. Things like the infinite self-energy of point charge, these things motivated researchers to look for alternative descriptions, maybe more field-based classical-like descriptions, even for fundamental particles. EED was one path people started exploring.
Gotcha. So, trying to smooth out some rough edges in both classical and quantum pictures. Okay, that sets the stage nicely. So, where are we now? What's the current state of play for ED research? Are these ideas getting more traction, more validation?
Okay, so this is where it gets, well, interesting and maybe a bit contentious. Research is ongoing. People are definitely working on refining the theories, exploring potential real-world uses.
I sense a but coming.
But yeah, it's really important to state up front. ED is still considered, outside the mainstream of physics. It hasn't been widely accepted or integrated into the standard textbook, so to speak.
Okay, so it's still more on the fringes, a theoretical exploration rather than accepted fact.
That's a fair characterization for the most part, but that doesn't mean activity has stopped. Not at all. There's definitely continued work. For instance, a significant recent paper, 2020, by Reed and Hively, Implications of Gauge-Free Extended Electrodynamics.
Reed and Hively. Okay, what did they find?
Well, they actually managed to derive ED from a different theoretical starting point, something called the Stueckelberg-Lagrangian. Now, that sounds super technical, I know.
A little bit, yeah.
But the important takeaway is that their work further developed the predictions around those scalar waves we mentioned, SLW and SW. And crucially, they suggested these waves wouldn't be subject to the skin effect.
Ah, the skin effect. Right, that's where, high-frequency electricity hugs the surface of a wire, doesn't really penetrate deep.
Exactly. So if these scalar waves don't have that limitation, well, Reed and Hively started thinking about what that could mean.
Which would be.
Some really intriguing possibilities, especially for things like wireless communication, maybe even transmitting power wirelessly without the usual energy losses you get at high frequencies because of that skin effect.
Wow. Wireless power without the waste.
That would be huge. Huge potential, yeah. Then, just a year later, 2021, Hively teamed up with Land for another paper, Extended Electrodynamics and SHP Theory, Stueckelberg-Horowitz-Piron Theory. Another one of these alternative frameworks trying to address perceived issues or inconsistencies in standard electromagnetism and quantum field theory. This paper suggested a potential link, maybe even an equivalence, between EED and SHP theory.
Okay, so trying to connect the dots, see if E fits into a broader theoretical landscape, maybe strengthen its foundations by linking it to other approaches tackling similar problems.
Precisely. Building bridges, finding common ground. And we should also mention A.I. Arbab's 2017 paper. He was looking at other ways to extend Maxwell's equations, too, like the Prococa equations and the Van Vleenderen-Weiser equations.
More alternative equations.
Yeah, and these often involve a pretty controversial idea, the concept of a photon that actually has mass. A tiny, tiny mass, but not zero.
Whoa, hang on. A massive photon. Doesn't the standard model definitively say photons are massless? That's, like, fundamental.
It is fundamental in the standard model, absolutely. And experiments put incredibly tight limits on any possible photon mass. It would have to be unbelievably small if it exists at all. But the idea of an effective mass can sometimes be useful, for example, in describing how light behaves inside certain materials, like superconductors.
Okay, an effective mass in a medium.
Ugh. And in the context of some of these extended theories, giving the photon even a minuscule hypothetical mass can theoretically allow for things like longitudinal waves, waves oscillating along the direction of travel, which are normally forbidden for strictly massless photons in standard theory.
So the mass, even if tiny and hypothetical, opens up new mathematical possibilities like longitudinal waves.
That's the theoretical motivation, yeah.
It really sounds like there's a lot of ongoing theoretical wrestling match happening here. Refining ideas, connecting theories. You mentioned institutions earlier, too, like the Bulgarian Academy of Sciences, EarthTech, even NASA getting involved.
Yeah, the Bulgarian Academy has that historical link through Donev's work. EarthTech International, which is often associated with physicist Hal Puthoff, has definitely explored these kinds of concepts, sometimes in connection with more, let's say, speculative applications like zero-point energy or advanced propulsion.
Right, Puthoff's name comes up in those contexts.
And NASA's interest, filtering through researchers like Larry Forsley, seems to connect ED to areas like lattice confinement fusion, or LCF. There's some thinking that ED might offer a framework to explain some unusual energy outputs or nuclear effects seen in those experiments.
Lattice confinement fusion. Oh, wait, I recognize that. We heard about LCF in the context of that Beyond Conventional Physics podcast, which was one of the sources you shared.
Exactly. And that's a perfect segue, because these recent discussions, like on that podcast and from the Convergence Summit, give us a fascinating glimpse into how some of these more theoretical ED ideas might actually be connecting with tangible cutting-edge technical developments happening right now.
Okay, so moving from theory towards potential practice. Let's dig into that. Where should we start? Unspace.
Yeah, let's start with Unspace and Philip Lentz. Their work is really focused on gravity, but with a twist. The core idea is that dynamic gravitational sources think really dense objects spinning very fast, like pulsars, or maybe even engineered objects, might warp space-time in a way that isn't uniform. It's not the same in all directions.
Not uniform. You mean anisotropic?
Exactly, anisotropic curvature. He proposes this could potentially explain some big cosmological mysteries like galactic rotation curves or certain anomalies in pulsar timing, things we currently attribute to, well, invisible dark matter.
So proposing a modification to gravity essentially driven by rotation and stress instead of just mass energy, that's bold. That's a big departure from standard general relativity.
It is a very significant departure. Yeah. And they're not just theorizing. Lentz and Unspace developed an experiment called EGAY. Yeah, it uses the highly sensitive torsion balance. Think of a delicate twisting setup. They use it to try and measure incredibly tiny changes or anisotropies in the gravitational field produced by spinning tungsten masses.
How fast are we talking?
Really fast, up to 50,000 RPM. The idea is that the stress and pressure inside that spinning mass, the centripetal tension, might be the source of this anisotropic gravitational effect they're looking for. They've run experiments searching for these directional gravity changes.
Okay, pushing the limits of measurement. And if they detect these effects, what are the potential applications they're thinking about?
Well, one of the most mind-bending ideas is the Resilient Gravitational Wave Communication System, or RGCS.
Gravitational wave communication, seriously?
That's the concept. The idea is that if you can create these anisotropic gravitational fields, you could potentially use them to create a sort of gravitational lens in space-time.
Like focusing gravity?
Kind of, yeah. Focusing or steering gravitational waves. And if you could do that, you might be able to send signals directly through matter, through the entire Earth, for instance. That would be incredibly secure, jam-proof communication.
Communicating with gravitational waves through the planet. Okay, my mind is officially a little blown. That's pure sci-fi territory almost. What other developments were highlighted?
Okay, let's shift gears slightly. We also heard from Richard Banduric of Field Propulsion Technologies. Their whole focus is propellantless propulsion, getting thrust without shooting mass out the back.
The dream of space travel, right?
Pretty much. Their approach uses novel metamaterials. These are materials engineered with tiny structures to have unusual electromagnetic properties. And crucially, they talk about breaking the electromagnetic gauges.
Breaking the gauges, what does that mean? Sounds deliberately provocative.
It does. Essentially, it seems to mean they're using a more complete mathematical description of electromagnetism, specifically involving the potentials, the scalar and vector potentials, in one of Maxwell's equations, without making the usual simplifying assumptions, the gauge choices, that physicists normally apply to make calculations easier.
So using a less simplified version of the math, hoping it reveals something new.
That seems to be the idea. And they claim that by doing this, they can design these metamaterials so that when you run an electric current through them, the internal forces, specifically ampere tension forces, get amplified and directed outwards.
Creating thrust.
Creating an external thrust, yeah. Opposite to the direction of the current flow. So it's a direct conversion, they claim, of electrical energy into motive force with no propellant needed.
And have they actually shown this works? Have they generated thrust?
The source material suggests they have demonstrated an external force generated by these metamaterials in experiments. And they're looking at a range of applications, things like space tugs, potentially collaborating with big names like Northrop Grumman and Sandia, but also maybe controlling hypersonic vehicles, strengthening materials, even advanced armor concepts.
Wow. Propellantless propulsion via metamaterials. That could absolutely revolutionize access to space and high-speed flight. Okay, who else? Hover Inc. Ankur Pat, also in propulsion.
Yes, Hover Inc. is also pursuing novel propulsion, but with a slightly different angle. They call it quantum propulsion.
Quantum propulsion, okay.
Their concept is a reactionless electric thruster. Again, no propellant. But their idea is to harness energy directly from the vacuum.
From empty space, the zero-point energy field.
That seems to be the claim.
Duh.
The key, according to them, is hyper-accelerating electrons. We're talking truly extreme accelerations. The figure mentioned is 10 to the power of 20 meters per second squared.
10 to the 20. That acceleration is just astronomical.
Within a specially designed capacitor-like structure. The theoretical idea, which they link to something called the Bott-Becker principle, is that this insane acceleration creates a gradient, a difference, in the vacuum energy field around the device.
And that gradient pushes the device.
The gradient generates a net force. The principle suggests the force is proportional to the square of the current and inversely proportional to the square of the distance between the electrodes, roughly.
And have they built anything?
Reportedly, yes. They've completed an SBIR Phase I prototype that's a government small business grant phase and claim it achieved measurable thrust over 2.5 millinewtons with very high efficiency, potentially over 200 newtons per kilowatt.
Tapping vacuum energy, that's another one of those holy grails, but often viewed with extreme skepticism. If it works, though, application.
Oh, huge potential. Think satellite station keeping without fuel limits. Long-duration asteroid mining missions where you don't run out of propellant. Maybe even enabling continuous acceleration for interplanetary or interstellar travel someday.
Okay, one more from the recent developments. Morningbird Space Corporation and Dr. Chance Glenn Sr. Their work sounded incredibly ambitious, trying to generate space-time distortions in the lab.
Yeah, very ambitious indeed. Their approach involves creating moments of extremely high energy density. They talk about 10 to the power of 12 joules per cubic meter.
How do they do that?
Using high voltage electrical spark gaps. Basically, very intense, very rapid electrical discharges. The hypothesis is that these sudden concentrated energy releases might actually cause tiny ripples or distortions in space-time itself, essentially generating miniature gravitational waves, or what they call wavelets.
Wavelets, I like that. Are they detecting anything?
They're using sensitive laser interferometers, similar in principle to the giant LIGO detectors that first found astrophysical gravitational waves, but on a lab scale. And the results apparently show subtle shifts, fringe movements in the laser patterns.
Correlated with the sparks.
Correlated with the timing and energy of the sparks? Yes. They interpret this as possible evidence that they are generating these localized space-time effects, these wavelets, driven by the rapid change in energy density, the DUT.
Generating gravitational waves, even tiny ones, in a lab. That would be revolutionary if confirmed. What are they thinking application-wise?
Dr. Glenn mentioned a whole spectrum. Propulsion, obviously. creating steerable arrays of these wavelet sources, maybe communication again, potentially even stabilizing fusion reactions, and some more speculative ideas about influencing biological processes.
Okay, so summing up this section, it really feels like while we might not have, commercially deployed ED-based warp drives just yet,
Not quite yet, no.
we are seeing some genuinely intriguing, maybe even successful early-stage demonstrations across this landscape. Unspace's experiments in communication concepts, field propulsion's metamaterial thrust, Hover's prototype, Morningbird's lab results.
That sums it up well. These are largely proofs of concept, early results, but they represent potentially significant steps in actually testing some of these unconventional physical ideas. And the fact that some are attracting attention, maybe even some funding from government agencies or industry partners, that's definitely noteworthy.
Absolutely. So looking further ahead then, stepping back to the bigger picture, if EID concepts or these related technologies continue to develop, if they gain more validation, what's the potential long-term impact? What could this unlock?
Well, the potential landscape is, it's really broad. Think about Unspace's ideas. Manipulating gravity could revolutionize communication, like we discussed, but also deep geophysical surveys, imaging inside the Earth, maybe countermeasures for GPS disruption, even methods for deorbiting space debris, or perhaps building better neutron guides for fusion reactors.
Okay, that's a lot just from the gravity angle.
Then you have the propellantless propulsion side from field propulsion and hover. If that pans out, it fundamentally changes space exploration, right? Makes missions cheaper, faster, enables missions that are just impossible today. Interplanetary travel becomes much more routine. Maybe even interstellar precursor missions become feasible.
A true spacefaring civilization starts to look more achievable.
Potentially. And Morningbird's work, if they can really generate and control these localized space-time effects or wavelets, that could open up entirely new ways to manipulate fields for communication, energy production, maybe even materials processing.
And let's not forget those earlier theoretical possibilities we touched on from gauge-free ED itself, wireless power transmission without the skin effect losses.
Right, potentially transforming energy grids.
And maybe new ways to model or interact with things at the nanoscale. Josephson junctions, molecular devices, even enhancing nuclear reactions in things like that lattice confinement fusion NASA's looking at.
Exactly. It feels like we could be just scratching the surface of some truly transformative possibilities, linking electromagnetism, gravity, maybe even nuclear forces in new ways.
But we have to inject a note of caution, right? What are the big hurdles?
Oh, absolutely crucial to remember the challenges. These are still, for the most part, unproven concepts in the eyes of the broader scientific community. The biggest need is for rigorous, repeatable, independent experimental validation.
Seeing is believing, basically.
Pretty much. Extensive testing is needed. And overcoming the, let's call it, healthy skepticism
Yeah.
within mainstream physics. That's a significant process. These ideas challenge long-held assumptions.
Sure. Extraordinary claims require extraordinary evidence.
That's the standard. It's a good one.
But even it's still an if. But if these hurdles can be cleared, the potential payoff seems enormous. Genuine breakthroughs in energy, communication, transportation, maybe even fundamental physics understanding.
The potential is undeniable. And it's fascinating just how interdisciplinary this whole area is becoming. You've got fundamental physics theory, bleeding-edge material science, advanced engineering, astrophysics, cosmology. It's all starting to potentially connect.
Yeah, it really breaks down traditional silos.
Absolutely. And for anyone listening whose interest is piqued, the resources are out there to explore more. The academic papers we've mentioned are often available online. There are books, conference proceedings, online discussions, those podcasts. The information is accumulating.
So wrapping things up, this deep dive into extended electrodynamics, it really unveils a fascinating, maybe even slightly wild frontier of physics, doesn't it?
It really does. It's a place where our basic understanding of a fundamental force, electromagnetism, is being actively challenged and potentially expanded. And the technological possibilities that could spin out of that, they're potentially revolutionary.
And even though, yeah, many of these ideas are still firmly in the theory stage or maybe just early experiments, the progress highlighted in the sources we looked at, these novel propulsion concepts, the gravity communication ideas, the lab results, it's undeniably captivating.
It really makes you wonder, doesn't it? What other secrets might the universe be holding on to? Just waiting for us to find the right key, the right theoretical lens.
It really does get you thinking, what if, communicating instantly across the globe or traveling through space without needing tons of fuel, what if that isn't quite as far-fetched as maybe we assumed?
Which brings us to maybe a final thought for our listeners to chew on. Could the key to unlocking some of the biggest, most persistent mysteries in the universe, things like galactic rotation, dark energy, maybe even understanding phenomena like UAPs, could it lie hidden within a deeper, more complete understanding of electromagnetism than the one we currently rely on?
A powerful question. What unseen forces, what hidden aspects of known forces might still be out there, just waiting for us to understand them and maybe even learn how to harness them?
Something to ponder.
Definitely something to ponder. We really encourage you to check out the resources related to today's discussion if this sparked your curiosity. And please join us again for future deep dives into other cutting-edge topics.